Okay, so let's get started. Yeah, before Easter, so we have been talking about essentially two things. So first one, as a user of a database, how can you query it, right? We talk about different type of query languages, including those theoretical ones, such as relational algebra, relational calculus, so on and so forth. We also talk about practical ones, the one that you can actually use in your database system. And we talk about different type of queries that you can write in SQL. And we actually been through the process of trying it in PostgreSQL, right? And then we talk about how can you use a database system to build the application you want. We decompose that process into a sequence of modeling steps. At the very, very beginning, you as a user have something in mind about what type of application you want to build. And the first step in the process is called conceptual modeling. That is for you as a user to write down precisely what are all the entities and relationships that you want to have in your application. And we talk about one way of doing that, and that is via entity relationship model. And one way for you to specify an entity relationship model is by drawing an entity relationship diagram, which is very similar to the one that you see on the left-hand side of the slides. After you have such a conceptual model, the second step is what we call logical modeling. And that is the step you take as input your conceptual model and implement that in the content of this course in relational model. And in relational model, all of your data are organized into a set of relations. Each relation has a schema, including the name, the set of columns or attributes, and also each relation also have a primary key, right? If you look at every single attribute, it is a combination of the name of the attribute or the domain of the attribute. For example, on the right-hand side, you can see one relation, which is students, which have 5 attributes. And then essentially when you have a relation instance of this relation, you can think about that as just fill in the content in this table. So the logical modeling step is the step that take as input the thing on the left-hand side and try to translate that into a thing on the right-hand side. And that is the focus of this lecture and also a couple of lectures after this. So when you do this type of translation, that is from a conceptual model to a logical model, and we talk about different ways for you to do it. And then we actually talk about different design decisions you can make when you do such a translation. And one thing that makes the whole thing a little bit tricky is actually continuity. Right? So let's refresh our memory about that. So here, assuming you have a conceptual model look like this, you have 2 entity sets, you have employees and you have departments, and they are connected by a relationship called works in, where an employee works in a department. And then you can see there's cardinality constraint here. There's a many-to-one relationship from employee to department, right? Which means that if I know the employee, I can uniquely identify a department. That is, one employee can only work in one department. How can we translate this into a logical model? Well, there are so many different things you can do. Let's consider the works in and employees relation, right? So the works in relationship will become a works in relation with 3 attributes. You have the social security number, you have the department ID, and you have since, right? And for employees, you have the social security number and you have the name. You could have this, right? This is a reasonable translation. But one thing that we talk about is you can actually merge these 2 into a single relation. Because you can see both of them has a primary key as social security number. When you do the translation, you could actually merge them into a single relation with 4 attributes instead. And we talk about these 2 different ways of designing the logical schema have different pros and cons, right? So when you do the merge, you are going to have essentially a single relation, right? Whenever I fetch a tuple there, I get all the 4 attributes. Whereas if you have 2 relations, if you want to fetch information of which employee works in which department, you always need to join these 2 relations, which could be very slow in a real-world database system. But on the other hand, if you have a whole bunch of employees without a department, right? If you merge them, you are going to have a whole bunch of null values, right, in the merged relation. So there are pros and cons, right? In real world application, you might want to pick the strategy that actually makes sense to you. And we also talk about a different case. So again, the same conceptual model, but let's consider the works-in relation and also the department relation, whether you can actually merge them or not. And in this case, as you can see, merging them in most of the cases doesn't really make much sense because they have different primary key, right? So the works-in relation has a primary key as social security number, and department relation has a primary key as department ID. When you join them, you end up have so many redundancies in the relation because every single time you put in a department ID here, you need to duplicate the relationship between the department ID and the budget. In many real world applications, merging these two relations are not always beneficial. So as you can see from these examples, given a conceptual model, there are so many different ways that we can translate that into a logical design. And from this lecture and also the couple lectures after this, the thing that we really want to understand is what is a good database design. And to answer that question, we want to formally model and enforce the properties that we want in a good database design. And that is what we are going to talk about today. So today we are going to introduce a notion called functional dependency, which will be the core of how to reason about a good design that we are going to keep getting back to in the next couple of lectures. Before we talk about functional dependency, let's look at one example. So let's look at this relation, storing the information about students. This is a relation with 5 attributes. You have student ID, you have the course the student takes, and one student can take multiple courses, right? For example, in this example, this student took 3 courses, so you have 3 rows in this relation. And then for each course, you have the grade. And then I have the name of the student and the address of the student. It's not hard to see that this is not really a good design, right? Because there are so many redundant information here. This student took 3 courses, so I have 3 rows, but the name of the student is independent to the course he takes. And in this case, I'm going to store in 3 copies of the name of students. I'm going to store 3 copies of the address of the student. And that could cause problems because once you have redundancy in your data, you could have so many different ways that you introduce an anomaly when you change your data. For example, you could have update anomaly, right? Like assuming the student kind of move to a new apartment, right? You need to update the address for this student. In this case, you need to update all 3 tuples. If you forget to update one of them, you end up having a database with inconsistent information. And when you try to insert example, and when you try to delete example, you can see this type of data redundancy is going to make all those update queries much, much harder to implement. So essentially, when we reason about the good design or bad design, a fundamental property that we want to understand is really data redundancy. We want to make sure when we model it, we eliminate as much data redundancy as possible, or at least try to understand what are all the data redundancies in the design, and then we can make an informative decision about whether the design is good or not for my application. Why do we care so much about redundancy, right? So there are multiple reasons. The obvious reason is it's going to waste storage space. I'm storing the information multiple times, right? So, but that's not often the most important one. So often the most serious one is that when you have redundancy, you need to have a very complex logic for updates, for insert, and for deletion, right? If you are not being careful, you will have inconsistent data. It's not about, it's kind of a little bit more expensive. You could save the data in 1 gigabyte, but you use 10 gigabytes. It's actually not like that. Once you have incomplete inconsistent information in your data, fixing them, clean them up is often more challenging than the waste of space. And that is a serious problem when you have data redundancy. So of course, when you have data redundancy, you could implement a more complex logic dealing with updates, dealing with deletion, dealing with insertion, but someone need to implement that logic. And often that is cumbersome if you really want to do that. On the other hand, right, redundancy may not always be a bad thing, right? So one thing that redundancy can actually help you is often to improve locality, right? Assuming you are building an application that every single time I fetch the course the student take, that I always need the name and address of the student. And assuming that is the only query you care about, in that application, this design might not be a bad one. Because every single time I read a single tuple here, I always get the name and address. That's the information I want. If I decompose into two relations, every single time I want to answer my query, I need to draw in the two relations. That could be slow, right? So redundancy could help you in some applications to improve locality. And sometimes storage is not a big problem. And sometimes you want to have some guarantees about fault tolerance and availability, right? I mean, you have multiple data centers. You want to make sure if one data center goes down, you still have your information. Right? In that case, you have to duplicate your information across different sites. Right? In that case, you have data redundancy, but it's going to help you on availability. Whether redundancy is good or not in your application is really a complex problem. But no matter whether it's good or bad, the goal of this lecture and a couple lectures after this is how can we model data redundancy and how can we reason about it? Because once we know how to reason about it, we can put that into your application and try to understand whether you want it or not. So that's the goal for this lecture. Specifically, we are going to be focusing on one type of data redundancy. And that is actually, you can see in this relation, you have student ID decide the name and address of the student, right? You cannot have one student ID connected to multiple names, right? If I know student ID, I must know the name. And you also have student ID and the course decide the grade. If you look at this relation, there's all those functional dependencies between different subset of attributes. And if you think about why this relation design have data redundancy, it's because you have so many of those functional dependencies that mix together in the same relation schema. And that is the type of redundancy we are going to look at in this lecture. And we are going to formally model it with a notion called functional dependency. So today we are going to talk about two things. First one is what are functional dependencies? And second is how to reason about them. By reason about them, we mean that you give me a whole bunch of functional dependencies that you know that hold in your application. How can we infer new functional dependencies out of that? So these are the two things we are going to talk about today. Okay, so now let's talk about functional dependency. Assuming I have relation R with the following schema, that is, I have 4 attributes A, B, C, and D, and each one of them has their corresponding domain, DA, DB, DC, DD. And the instance of this relation is a subset of tuples, and each tuple is drawn from the cross product of all the 4 domains. Let's say we have 2 subsets of attributes, alpha and beta. So from now on, when we see alpha and beta, we always mean a subset of attributes. Whenever we see A, B, C, D, right, we always mean a single attribute. So here, assuming you have 2 subsets of attributes, alpha and beta, we see there's a functional dependency from alpha to beta. And sometimes you can also say beta is functional dependent on alpha, right? So sometimes it's just easier to say there's a functional dependency from alpha to beta. If and only if the following is true. That is, for all pair of tuples, R and S in R in relation instance, if R and S match on alpha, it implies R and S also match on beta, which essentially says that if you have a relation instance R, and if this R satisfies the functional dependency alpha to beta, it means that if I know the value on alpha, it will decide the value on beta. That is, I cannot find a pair of tuples R and S such that they match the value on alpha, but they have different beta values. And if that is true, we write in this way. That is, R satisfies this functional dependency from alpha to beta. And this is the definition of functional dependency. Let's look at one example. So here is one relation instance R with 4 attributes, right? So let's try to find functional dependency here. So if you look at the first functional dependency from A to B, right? So and you can see this relation R actually satisfies this functional dependency. Why? Because if you look at the A value, a single value in A will only map to a unique value in B. So A4 map to B4, and there is no other tuple in this instance with the same value A4, so it's fine. If you look at A1, there are 2 tuples share the same value, but both of them will map to the same value, that is B1. You can look at A2, you can look at A3, but essentially in this relation instance, if I know the value of A, I will know the value of B. I can uniquely decide a single value in B corresponding to A. That is why in this relation, it actually satisfies the functional dependency from A to B. It also means in this relation instance, B is functional dependent on A. Okay, so these are just different ways to spell out this mathematical formula. So now let's look at the second functional dependency from CD to B. Right? In this case, this relation instance also satisfies that. Why? Because if you look at the combination of C and D, every single unique combination will map to a unique B. You do not have 2 tuples with the same value on C and D, but have different value on B. You can check that by yourself. So that is why we say in this relation instance, this functional dependency from CD to B is satisfied. Now let's look at another example. Let's look at the functional dependency from B to C, right? In this case, as you can see, I have 2 tuples sharing the same B value, but they map to different C values. You have B2, C3, B2, C4, right? So that's the reason that in this relation instance, it does not satisfy this functional dependency. You cannot have B to C for this relation instance because given a B, you cannot uniquely identify a single value in C, okay? So let's also talk about one notation convention, right? Sometimes when you have like multiple attributes on the left-hand side or right-hand side, we just do not write them as a set. We just write them in this way, CD to B, instead of the set CD to set B. Okay, so it's just a convention of notation to make that like a little bit simpler to write. Okay, so now we know what is functional dependency. Let's look at another example. So this is a relation containing information of a family tree. Right? You have 5 attributes. You have child, father, mother, grandmother, grandfather. Let's try to find a functional dependency here. First one, you have the functional dependency from child to father and mother. Right? In this relation instance, given a child, you can uniquely identify a father, uniquely identify a mother. That is true for this relation instance. On the other hand, you also have the functional dependency from child grandfather to grandmother, and also from child grandmother to grandfather, which means that if you tell me the child and the grandmother, I can uniquely identify in this relation instance, the grandfather. And if you give me a unique configuration between child and grandfather, I can also uniquely identify a grandmother. So these are the example of functional dependencies that this relation instantly satisfies. If you are curious about why do we call them functional dependency, right? So the reason is it's very similar to a function. So let's assume you have a function f1 that simply take as input the child and output its father. This type of kind of mapping between different values is exactly what the functional dependency is trying to model. Whenever there's a functional dependency, for example, from child to father, it actually means there exists some function that take as input child and output father. Because in functional dependency, a unique child will always correspond to a unique father. You can always have a function to encode that piece of information. Otherwise, you cannot have a function because a single child may have different output values, right? Because of this, this is actually where the name functional dependency comes from. It's actually work very similar to a function. So once we know definition of functional dependency, how can we use it? Well, we can finally formally define what a key is. So let's say you have a subset of attributes, alpha. We say it is a super key if and only if there's a functional dependency from alpha to all the other attributes in R, which essentially means that if you gave me a value on alpha, I can uniquely identify the values for all the other attributes in relation R. If that is true, we call alpha is a super key. And we say a functional dependency from alpha to beta is minimal if and only if you remove any attribute on the left-hand side from alpha, you do not have the functional dependency to beta anymore. If that holds, we say the functional dependency from alpha to beta is minimal. And what is a key, right? So a key is essentially this. If alpha is a key, it means that you have a minimal functional dependency from alpha to the rest of the attributes in the same relation. So essentially, if all the other attributes in R minimally functional dependent on alpha, then alpha is a candidate key. So this is a precise definition of key using functional dependency. If a set of attribute alpha is a key, it means two things. First one, there's a functional dependency from that attribute to the rest of the attributes. And second, that functional dependency is minimal, meaning that if I remove any of the attributes from that set, I will not have that functional dependency anymore. If these two conditions hold, then that subset of attributes alpha is one candidate key. Okay. So let's look at one example. So here you have a relation storing information about different towns, right? You have a name, you have canton, you have area code, you have population. So let's try to find a functional dependency here. We first have the name and the content together, decide the area code and the population, which makes sense, right? And we also have the name of the town and the area code together, decide the content and the population, which also makes sense. And because of this, there are two possible keys in this relation. The combination of name and content could be a key because there's a functional dependency from this pair to the rest of attributes. And also that is minimum. If you remove one of them, that functional dependency doesn't exist anymore. And then you have another candidate key as the combination of name and area code because of the second functional dependency. So another interesting is about cardinality, right? So let's just refresh our memory about cardinality in entity relationship models. So here we have an ER diagram with three entity sites. You have lecturer, you have professor, you have department. They participate in a three-way relationship teaches, okay? So this cardinality constraint means that if I know lecturer and professor, I can uniquely identify a department. If I know lecturer and department, I can uniquely identify a professor. So what this categomatic constraint is doing under the cover is to define a whole bunch of functional dependencies that's going to hold in this application. For example, if you give me this entity relationship diagram, it actually defines these two functional dependencies. That is, there's a functional dependency from professor, lecturer to department, which means that if you give me professor and lecturer, I know the department. There's a functional dependency from department, lecturer to professor, which also makes sense. What this diagram does not tell us is, so another thing that this diagram tells us is there's no functional dependency from lecturer to department and professor, simply because by reading this, I cannot have this, right? So cardinality is a way for you to introduce functional dependency in your application. And these functional dependencies is going to determine the keys, right? Because we already defined key via functional dependency. Another thing to keep in mind is not all of the functional dependencies are derived from cardinality information, but cardinality information is a very popular way for to introduce functional dependency into your application. So now we go through the definition of functional dependency. Let's try to look at one fundamental question. That is, assuming I already know a whole bunch of functional dependencies that is in my application, how can I infer new functional dependencies from this? So what is our goal? Our goal is actually very simple. The input we have is a set of functional dependencies F that we know hold in my application. The question is, how can we find new functional dependencies that can be implied from this set of functional dependencies? And we call that process inference. So there are multiple fundamental questions. But one question is that if you give me F, the set of functional dependencies, and you give me a different functional dependency from F to beta, will alpha to beta hold given F? That is actually the question we want to understand. But to understand that fundamental question, we have two things. We need to first define what do we mean by alpha to beta hold, or we have alpha to beta given F. Like all the reasoning systems, there are actually two ways to define it. The first way is semantic. And we write in this way. Given F, you can actually imply alpha to beta. It essentially means that for any relation instance R that satisfies F, it also satisfies alpha to beta. If this holds, right, we mean that you have alpha to beta given F. So this is a semantic way of defining that. And then there's a syntax way, right? So, and here we write in this way, right? Alpha, F to alpha and beta, right? So that simply means that you give me a set of inference rules, and by applying it to F, I can finally derive alpha to beta. That you give me a whole bunch of axioms. By applying those axioms again and again over F, I will derive or prove alpha to beta. If that is true, right, we can also say that you have alpha to beta given F. Right? Like most of the reasoning type of system, you have the semantic, you have the syntax, right? About what you mean by you can imply alpha to beta given F. One fundamental result that we have is you can construct a reasoning system with three very simple axioms called Armstrong axioms. And by applying those axioms again, you have the reasoning system. And the fundamental result is under that reasoning systems, the semantic and syntax are equivalent. That is, the Armstrong axiom, the reasoning system, by applying that, is both complete and sound, which means that for any functional dependency alpha to beta that hold semantically, you can derive a derivation by using Armstrong's axiom. And also for all the functional dependency that you derive by applying Armstrong axioms, they are also semantically sound in the sense that semantically they also hold. So this is a fundamental result about the inference of functional dependency that we are going to look at for the rest of the lecture. Okay, so now let's look at semantic first, right? So let's try to define more precisely what do we mean by semantically a set of functional dependencies imply another functional dependency. So let F be a set of functional dependencies on schema R. We have another functional dependency from alpha to beta. We say F implies alpha to beta, and we write in this way, yeah, F and this symbol alpha to beta. If every single relation instance R of this schema that satisfy this set of functional dependencies in F also satisfy alpha to beta. Okay, here let's replace F to alpha to beta. There's a typo. And also, we can define another notion called closure. Okay, so let F be a set of functional dependencies on schema R, and then the closure of F, we write it as F plus, is a set of all functional dependencies that can be implied by F. Okay. And then if you give me two sets of functional dependencies, now I can define their equivalency, whether they are equivalent or not. We say two sets of functional dependencies on the same schema are equivalent if you can, if F imply G and G also imply F. Okay, if both hold, right? So you have two equivalent set of functional dependencies. This is at the semantic level, what we mean by one functional dependency or one set of functional dependency imply a new functional dependency or imply a new set of functional dependencies. So one fundamental question that we want to understand is that is there a systematic way to compute the closure? That is, you give me F. Is there a systematic way for me to compute all functional dependencies that can be implied by this set F? Is there a systematic way to do such inference? Is there a systematic way to check that given a set of functional dependency F, whether it can imply a new functional dependency, or if you give me two sets of F and G, is there a systematic way for me to check whether they are equivalent or not? And this question will motivate our study on our inference system to really try to say, given F, how can we systematically prove another functional dependency is going to hold or not? And that reasoning system, to answer the question, is a reasoning system that's constructed by what we call Armstrong's axiom. It is a three very simple rule for you to derive new functional dependencies given a set of existing functional dependencies. So there are three rules. The first rule is reflexivity, which means that if you give me two subsets of attributes, alpha and beta, and alpha is a subset of beta, it implies there is functional dependency from beta to alpha. Okay. One special case is if you take beta as the set of all the attributes, is R, it implies that you have functional dependency from all the attributes to a single attribute. So, and also we call all of these functional dependency where the left-hand side is a superset of the right-hand side, trivial functional dependencies. So another inference rule is what we call augmentation, which essentially, if you have a functional dependency from alpha to beta, it implies that you have a functional dependency from alpha gamma to beta gamma. That is, you can add the same set of attributes both to the left-hand side and the right-hand side, and that's going to be fine. So here we use a simple notation that alpha gamma means alpha union gamma. Okay? And the third inference rule is transitivity, which means that if you have alpha to beta and beta to gamma, you will also have alpha to gamma. Okay, it's very simple. what's interesting is that the reasoning system constructed by these three axioms are both complete and sound, which means that all possible other functional dependencies that can be implied given a set of functional dependency can be derived by applying these three axioms again, and again. So now let's look at each of these axioms, and then let's try to prove that the reasoning system constructed by these three axioms are both complete and sound. So the first axiom, reflexivity, right? It simply means that if alpha is a subset of beta, then you have beta decide alpha. So let's look at why does this axiom make sense, right? So why does this one give us something that is semantically sound? That is, if I infer functional dependency using this axiom, why would that give me something that can be semantically implied, okay? So to do that, right? So let's assume you have two subsets of attributes, alpha and beta. Essentially, we hope to prove that if you give me two tuples, T1 and T2 in any relation instance R, if they match on beta, it's also match on alpha, okay? So that is something that we want to prove. And as you can see, you can always prove that no matter what R you have, right? So let's say you have T1 and T2 be two arbitrary tuples such that they match on beta. Now we can prove by contradiction, right? Let's assume they do not match on alpha, right? This actually implies there exists a colon C on which T1 and T2 mismatch, right? Because C is a one element draw from alpha, and that always exists. And because alpha is a subset of beta, right? Then C is a subset of beta, then C also belongs to beta. And therefore, we know T1 and T2 cannot match on beta. That contradicts our assumption, right? We must have T1 and T2 match on alpha. So what this shows is that assuming I have alpha and a beta, and alpha is a subset of beta, semantically, I always have the functional dependency beta to alpha can be implied, right? So essentially, applying this Armstrong axiom will give me something that makes sense, right? So another rule is augmentation, right? Which is simply means that if you have alpha to beta, I can apply this rule to derive alpha gamma to beta gamma. But the question is, yes, you can apply this rule to derive a new functional dependency, but does that give you something semantically sound? Which means that if I have a relation instance that satisfies alpha to beta, do I always have, I have that relation instance satisfy alpha gamma to beta gamma? Whether applying this inference rule is going to give me something that is semantically correct. So this is also easy to prove, right? So again, we prove by contradiction, and we assume that first, there's a functional dependency from alpha to beta, and we assume on the other hand, you do not have functional dependency from alpha gamma to beta gamma. And because you do not have functional dependency from alpha gamma to beta gamma, you must have the following as true. That is, you can find a pair of T1, T2 such that they match on alpha and gamma, but they do not match on beta gamma. If you cannot find this pair, it means that there is a functional dependency from alpha gamma to beta gamma, right? But because you are assuming alpha gamma to beta gamma is false, you can always find this pair. So once you find this pair, you will know that this pair T1, T2, they will match on alpha, right? Because they match on alpha gamma, they must match on alpha. And because you know there's a functional dependency from alpha to beta, it means that like these two tuples must also match on beta. However, that contradicts with this condition, right? So essentially, you have the contradiction, right? So essentially, you prove that you cannot have the case where you have alpha to beta, but you do not have alpha gamma to beta gamma. Okay. So the third axiom, the inference rule, is transitivity. If you have alpha to beta, beta to gamma, right, you can apply this inference rule to derive a new functional dependency that is alpha to gamma, right? But the question is, does this rule give you something that is semantically sound? That is, if I have a relation instance that satisfies alpha to beta and beta to gamma, does this relation instance always satisfy alpha to gamma, right? That is something we want to prove. So the proof is actually very simple, right? From alpha to beta, we know that for all tuple T1 and T2, if they match on alpha, they also match on beta. From the functional dependency beta to gamma, we know for any pair of T1, T2, if they match on beta, they also match on gamma. If you combine them together, you know for any pair, if they match on alpha, it will also match on gamma, right? So essentially, for any relation instance that satisfies alpha to beta, beta to gamma, that relation instance will always satisfy alpha to gamma. That is, if you apply this inference rule to derive alpha to gamma, given alpha to beta and beta to gamma, you will have something that is also semantically correct, okay? So if you put these three rules together, right, all of their semantic soundness are simple and natural, but what's amazing out of this is putting these three axioms together will give you an inference system that is both complete and sound. And that's something we are going to look at. So first, before we talk about soundness, let's try to formally define what do we mean by that. So let's there be a functional dependency, a set of functional dependency F on schema R. We say this functional dependency, set of functional dependency F derives a new functional dependency alpha to beta. And we write in this way, F and this symbol alpha to beta. If there's a derivation for alpha to beta by only using Armstrong's axioms, that is, you take F and you keep applying Armstrong's axiom to F, then you can derive alpha to beta at the end. If that is true, we say F derives alpha to beta. And on the other hand, we have the semantic notion. That is, we say a function set of functional dependency F implies alpha to beta, written this way, F implies alpha to beta. If every single relation instance of R that satisfy all functional dependencies in F also satisfies alpha to beta. So by soundness, we mean the following. For any functional dependency alpha to beta that can be derived using Armstrong's axiom from F, you will have semantically F imply that alpha to beta. So that is what we mean by soundness. That is, for any single rule that I can derive by applying this whole bunch of axioms, they will be semantically correct, okay? This is relatively easy to see. So and you can prove by induction, right? So you start from a formula that can be derived using K-1 applications of Armstrong's axiom. And then we already proved the semantic soundness of each of the axiom, right? You will actually have applying at the K times, right? We will also give you something semantically correct. What's a little bit tricky is on the completeness side. So what do we mean by this? Essentially, we mean the other way around. That is, if you have a set of functional dependency F, and that implies semantically a new functional dependency alpha to beta, which means that for any relation instance R, if it satisfies F, it will also satisfy alpha to beta. If F implies alpha to beta, then you can derive alpha to beta given F by applying again, one of the three axioms, like Armstrong axioms. You can derive that using Armstrong axioms if you can semantically imply alpha to beta from F. This is a little bit tricky to prove, but let's try to think about it. Before we talk about the proof, let's introduce another notion, which is a closure of some attributes. So let F be a set of functional dependency over R. And let's say alpha is a subset of attributes of R. We see the closure of alpha with respect to F, and we write it down as alpha plus. It's a set of all attributes Y such that the functional dependency from alpha to Y can be derived from F using Armstrong's axioms. That is, the closure of alpha is all the other attribute Y for which you can derive alpha to Y given F. Okay, so essentially this is all the right-hand side of functional dependencies that you can prove using Armstrong's axiom. And we call that the closure of alpha. Given this notion, right, so there's a very simple statement that we can prove. That is, if you can derive alpha to beta by applying Armstrong's axioms given F, that is equivalent to beta is a subset of the closure of alpha. Now let's try to prove this. It's actually very simple to prove. You first prove from left to right, right? Assuming that you have given F, you can derive alpha to beta by applying Armstrong's axiom. And you gave me any Y in beta. And I want to prove that Y is part of the closure, okay? So in this case, right, you first have recessivity, right, which is given F, you can derive alpha to Y, so you can derive beta to Y, right, because Y is part of beta. And you have transitivity, right? You already have alpha to beta, you have beta to Y, then you can actually derive alpha to Y, right? And then by the definition of closure, right, Y is going to be part of the closure of alpha. On the other hand, it's a little bit tricky. So assuming you have beta as a subset of the closure of alpha, we want to prove that for any attribute in beta, you can actually derive the functional dependency from alpha to that attribute, right? So for any Y in beta, you can derive alpha to Y. So here, it's kind of not that hard to prove. So first, you want to prove the following statement that if you have functional dependency from X to Y, and you have functional dependency from X to Z, that implies you have functional dependency from X to YZ, okay? You can prove that by just going back to the definition of functional dependency. And given that, for any attribute Y in beta, right? If you have, you can derive alpha to Y, this also means that you can actually derive alpha like to beta, right? So like given this, right? So you actually prove this very simple statement. That is, if you can derive alpha to beta from F, then beta must be a subset of the closure of alpha. And given this, we can actually ready to prove the completeness. It's actually not that hard to prove. So suppose we have that you can semantically imply, right, alpha to beta from F. That is, for any relation instance R that satisfies F, it will also satisfy alpha to beta, assuming you have this. But you do not have the right-hand side. That is, you do not have, that you cannot derive alpha to beta from F. Assuming this is true, and we try to derive a contradiction, we know that beta cannot be a subset of the closure of alpha. Why? This is because this statement we just proved, right? So beta cannot be a subset of closure. It means that beta must contain some attribute that's not in the closure of alpha. And our goal is to construct relation instance R such that F hold in R, but alpha to beta does not hold in R. And this will give us a contradiction. So let's look at this relation, okay? So you have relation R with two subset of attributes. You have the fourth subset of attributes which is the closure of alpha plus, right here. And then you have all the other attributes. And then let's talk about one relation instance that have two tuples. And these two tuples have the same value on the closure of alpha, both of them 1. And then they have different values on all the other attributes. So let's consider this relation R. So there are two things we want to prove. One thing is that this relation instance R does not satisfy alpha to beta. Right? So how can we prove it? Right? I mean, in this case, alpha is a subset of its closure, right? So the alpha, like always a subset of the first, of the closure, right? So the alpha column will always be here, right? So, and the beta is not a subset of alpha plus. It means that for beta, you will have some attribute on the right-hand side. In this case, you have two tuples share value on alpha by construction, but they have different values on beta, right? So it's very simple. This relation does not satisfy alpha to beta. And the second step is try to prove that this relation R satisfies F, okay? So in this case, suppose you have one function dependency, gamma to theta in F. So there are only two cases. Either gamma is a subset of the closure, or gamma is not a subset of the closure. So for each of the case, you can actually go through the exercise and you can see why this relation R is going to satisfy like this kind of functional dependency gamma to theta. Okay, so combine these two things, right? So you construct the R that satisfies F, but does not satisfy F to beta, which means that F will not imply alpha to beta. That contradicts with our assumption, and then essentially you'll prove the completeness. So this is a very quick walkthrough of the proof of completeness. Okay? So that is what's amazing about the inference system constructed by Armstrong axiom, that it is 3 such simple rules, but applying them again, you will have an inference system that is both complete and sound. So given that, we can actually derive new rules about functional dependency. So let's look at some examples. So assuming I have functional dependency from alpha to beta, and I have functional dependency from alpha to gamma. One thing that we can prove is this will imply there's a functional dependency from alpha to beta gamma. You can actually union the right-hand side. So to prove this, you can always go back to definition. But here, let's try to prove it using Armstrong's axiom because we know it's complete and sound. Right? So you first have, there's a functional dependency from alpha to beta. This is given. And then you have alpha to gamma, which is also given. And then you can do the augmentation by taking the second rule, alpha to gamma, and you augment it by alpha on both hands, right? So you put alpha on the left-hand side, you put alpha on the right-hand side, then you have a new functional dependency from alpha to alpha gamma. You get the third one by doing augmentation or the second one. And then you can do another augmentation of the first functional dependency. You take alpha to beta and you augment it using gamma. You put gamma on both the left-hand side and the right-hand side. And you take the third one and the fourth one, and you apply transitivity. Then you have the functional dependency from alpha to beta gamma. So as you can see, this is one derivation using Armstrong's axiom that gave you at the end alpha to beta gamma, right? And because the inference system constructed by Armstrong axiom is both sound and complete, if I can have such a derivation, it actually means that semantically, you can actually imply the last functional dependency given alpha to beta and alpha to gamma. So let's look at another rule, right? That is, assuming I have the functional dependency alpha to beta gamma, can essentially semantically imply you have both alpha to beta and alpha to gamma. Again, so you can go back to the definition for this. Let's try to use Armstrong's axiom. It's actually very simple, right? So as a condition, you have the functional dependency from alpha to beta gamma. And then by reflectivity, you have the functional dependency from beta gamma to beta. Right? Why? Because the left-hand side is a superset of the right-hand side. And then you do transitivity, you have alpha to beta. Right? And similarly, you can prove that for alpha to gamma. So as you can see, once we have Armstrong's axioms, once we prove that the redundant system is complete and sound, it's very easy for us to derive new rules related to functional dependency. So let's look at one a little bit. It's not that hard, but a little bit more complex. It's about the pseudo transitivity, which means that if I have alpha to beta, and then I have beta gamma to theta, we'll also have alpha gamma to theta. Okay, so how to prove it? It's actually very simple. You have alpha to beta, which is given, and then you do one augmentation to have alpha gamma to beta gamma. Since I already know beta gamma to theta, which is given, put them together, applying transitivity, you have alpha gamma to theta. Right? So as you can see, once we have the redundant system, it's very easy for us to derive new rules about functional dependency. So this is about Armstrong axioms, its completeness and soundness, and how to apply it to derive new rules. So let's talk more about the closure because that's interesting. Let's refresh our memory, right? What is closure, right? Of a set of attributes, right? So let's F be a set of functional dependency over this schema R, and alpha be a set of attributes of R. The closure of alpha with respect to F, and we call that alpha plus, is essentially it's all the Y that you can derive alpha to Y from F. Okay. So the question is, now I give you a set of functional dependency, F over R, and I give you a set of attributes alpha. How can we systematically construct alpha plus? So here's one algorithm for you to do that. So we will start from alpha plus equals to alpha, because we know every single attribute alpha, in alpha will always in its closure, right? So, and we repeat the following thing. That is, we, for each functional dependency, beta to gamma in F, we check whether the left-hand side, that is beta, is already in the closure. If it is already in the closure, we then add gamma to my new closure, right? Which means that I can kind of derive alpha to gamma, right? So because I can derive alpha to whatever in the closure, beta is part of the closure, so I can actually derive alpha to gamma. So I put the gamma together with my current closure and I get a new one, right? I keep doing this until I cannot make alpha plus larger. And when that happens, I will output alpha plus. So as you can see, this is a very, very simple algorithm for to calculate the closure of alpha with respect to F. Okay. So once you have such an algorithm, so there are a lot of things you can do. First one is if I give you a set of functional dependency F, and I want to ask you, okay, can F derive alpha to gamma? Then what should you do? Now we have a systematic way to do it. You first calculate the closure of alpha with respect to F using that very simple algorithm, and you check whether gamma belongs to the closure or not. If it belongs to the closure, it means that I can derive alpha to gamma from F. Otherwise, it means you cannot. And you can try to check whether a set of functional dependencies, F can derive another set of functional dependency G, right? By going through every single functional dependency alpha to gamma in G, and you check whether F can derive that functional dependency or not. And you can check whether a set of functional dependencies F is equivalent to another set of functional dependencies in G or not. So how to do this, right? you first check whether f can derive g, and you also check whether g can derive f or not. Now we can also check if a subset of attributes k is a super k or not, given the set of function dependencies f. So how to do it, right? You first check whether you can derive k to r given f using a very simple algorithm, right? And then you try to check. Yeah, so that's the only thing you can. That's the only thing you want to check. If you want to check whether super k or not. If you want to check whether k is a key or not, you need to check both this and whether it is minimal, right? So that is, if you remove any attribute in k, do you still have this function dependency or not? Okay. So as you can see, all those questions can be answered easily given an algorithm to compute the closure of f of class. And in the previous slides, we already gave you one such algorithm. Okay, so this is about the closure. So another thing that we want to understand about the function dependency is a notion that we call minimal basis or minimal cover, which will become very useful in the next lecture. But here we will talk in a really abstract way. So let f be a set of function dependencies. So look at this example. You have the function dependency from A to BC, from B to D, and from A to D. One observation that we can have is not all of these function dependencies are necessary, right? Because if you gave me the first two, A to BC, B to D, I already know A to D from these two, right? So you do not really need to specify A to D for me. So that is the motivation for us to introduce the notion of minimal cover. That is, if you give me a function, a set of function dependency f, I want to simplify it by removing redundant function dependencies such that I do not change this set f. I can get something semantically equivalent, but much more simpler. So that is our goal. And that simplified version of this is what we call a minimal cover of f. So let f be a set of function dependencies, and then the minimal cover of it, let's say as g, has a following property. First one, g is equivalent to f. Okay, so that's very important. By simplify it, you do not change its semantic. And second, all the functional dependencies in g have the form from x to a, where a is a single attribute. Your right-hand side is always a single attribute. And third, it's not possible to make g smaller. What do we mean by that? We mean you cannot delete a functional dependency from g. Once you do it, you will not have something semantically equivalent. You cannot remove functional dependency from g while keeping the semantic. And second, for any single functional dependency in g, you also cannot change anything from the left-hand side. You cannot remove one attribute from the left-hand side of some function dependency g, but still keep the semantic. So if g satisfies all the three conditions, then we say g is a minimal cover of f. And the intuition behind it is very simple, right? G is a set of functional dependencies that's minimal in the sense that I cannot remove anything. I cannot remove a functional dependency from G. I cannot remove anything from the left-hand side, and the right-hand side of G is always a single attribute, right? It's really the simplest thing I can have, but still semantically equivalent to F. That is intuitively what I want to enforce by having the minimal cover. So how can we compute the minimal cover or minimal basis? So you can have an algorithm with multiple steps, and in the textbook, there is a very precise algorithm to do it. So the first step is you have G, you construct G by taking all the function dependencies in F and decomposing the right-hand side to a single attribute, right? And second, you remove functional dependencies that are trivial, right? Which means the left-hand side is a superset of the right-hand side. And then you remove all redundant attributes from the left-hand side of function dependency in G. How to do that? For every single function dependency in G, let's say that's x to y, you take each attribute in X, you remove it, and you see whether you can still derive the functional dependency x minus x decide y. If that is true, you replace your old functional dependency x to y with this smaller y. Okay. And step number 4, you remove from the current set of functional dependencies all the functional dependencies that can be derived given the rest of functional dependencies. So I know this looks a little bit abstract, but you can actually go to the textbook. There is a concrete algorithm for to compute the basis. So as an example, right? Assuming I have a set of functional dependencies with these 4 FDs, A, B to C, A to B, C, B to C, A to B, right? So the first step is I will make the right-hand side consist of only a single attribute, right? I will take A to B, C and decompose it into A to B and A to C. And then I will remove trivial functional dependencies. In this case, I don't have that, so I move to the third step, right? And then I try to make the left-hand side smaller, but still keep the same semantic, right? So in this case, it turns out if I take A, B to C, if I remove A, nothing will change, right? So I can actually replace that to a simpler one like B to C, right? And then I remove all the redundancies, and I get my basis. Right? So this is just a very simple illustration of the algorithm. So again, it's very hard for us to cover the process algorithm in the lecture. When you go back home, try to read the textbook. So there's a very concrete algorithm there for to compute the basis. It's a very important notion. We are going to use it in the next lecture. So make sure you know how to compute that, okay? So again, like many concepts we have in this course, the best way to learn it is actually to practice. So here's a very good website that if you give it a whole bunch of functional dependency, it's going to walk you through step by step how to compute its basis. When you go back home, just construct some examples using this tool. It's very easy to learn how to compute the basis. Right? You just need to practice it for multiple times, then you are fine. Okay. So this is about basis. So another thing we want to understand is, given our understanding of functional dependency, one thing that's interesting is we can now kind of reason about decompositional relations. So in this lecture, we are going to talk about it in a little bit abstract way. Okay, so in the next lecture, it's going to be concrete about why do we even talk about decomposition. So what is decomposition? Right? So intuitively, right, if you think about all those bad logical designs, right? So sometimes those bad designs is because you have one relation that contains multiple concepts, right? So think about our previous example. You have a student name, address, and the lecture and the course the student took and the grade, right? So you have multiple things mixed in one relation. So one thing we want to understand is whether we can decompose a large relation into multiple smaller ones. Essentially, your input is R on the left-hand side, and I want to decompose it into a whole bunch of smaller relations, R1 to Rn. And I want to understand what are the properties of the decomposition and whether they are always possible or not. So there are two types of decomposition we are curious about. The first type is what we call lossless decomposition. In this case, it means that if you have relation R, if you decompose it into R1 to Rn, if you join them together, you join R1 to Rn, I can fully recover all the information in R. If that is true, and we say R1 to Rn is a lossless decomposition of R. And second property of decomposition is the preservation of dependencies. That is, I decompose R into R1 to Rn, and each of them have functional dependencies. If I take all those functional dependencies from R1 to Rn and union them together, I calculate the closure, whether the closure will be the same as taking all the functional dependencies from R and calculate the closure. If this holds, we say this decomposition is going to preserve all the functional dependencies. So these are the two properties of decomposition that we want to reason about. So let's look at the lossless decomposition property first. When is the decomposition lossless, right? So let's think about this. You have relation R, and you decompose it into R1 and R2. And consider decomposition. You have R1, which you take R and do a projection on R1, you get R1. And then for R2, you do a projection on R2, okay? So let's say this is decomposition. We want to understand when will this decomposition from R to R1 and R2 is lossless. That is, when would that happen if you join R1 and R2, you can fully recover the information of R. So in this case, right? So if you have the intersection of R1 and R2, those set of attributes, functionally decide R1, or you have that intersection functionally decide R2, we can say this decomposition is actually lossless. And so you have one relation R, right? So we have three set of attributes. We have alpha and beta is in R1, beta and gamma is in R2 in the decomposition. If you have a functional dependency from beta to gamma, or have a functional dependency from beta to alpha, this decomposition will be lossless. Okay, so it's very easy to see, right? Because if I have the functional dependency from beta to gamma, when you join R1, R2, right? So you actually fully recover the information, right? So let's look at one example. In this example, I have a relation contains three attributes, right? I have the pub, I have the guest, and what this guest drink in this pub type of beers, right? So assuming I want to decompose it into two relations, visitors and drink. The first relation is going to take the pub and the guest. The second relation take gas and beer. This is one decomposition. And whether this decomposition is lossless or not. Now to check that, right? So you just join them together, right? And you can see this decomposition actually not lossless. Well, you are going to, after you join them, you are going to have all those additional tuples that does not appear in the input. So this decomposition is not lossless. Why? If you think about this, is that you do not have any of these two functional dependencies. You do not have the functional dependency from gas to beer. You do not have the functional dependency from gas to pub. And because of this, if you decompose it, you will not have a lossy decomposition. Once you join them back, you will have more tuples. Okay. And this is another example about decomposition. Assuming I have a relation parent contains three attributes, father, mother, and child. And then I decompose it into two relations, father and mother. So the father relation will contain father and child, mother relation will contain mother and child. Will this decomposition be lossless? In this case, as we can see, if you join them together, you are going to recover all the information in the input. If you think about why, it's in the original relation. You have the functional dependency from child to mother. You also have the functional dependency from child to father. And because of this, once you do the decomposition and join them back, you will preserve all the information in the input. So another property that we want to reason about when you decompose a large relation into a whole bunch of smaller ones is their preservation of functional dependencies. So let's say you have a relation R and you decompose it into R1 to Rn. We say this decomposition preserve functional dependencies is if the following is true, that is you take all the functional dependencies in R, you calculate the closure, and that set is the same as you take all the functional dependency from each of R1 to Rn, you union them, calculate the closure. If these two closures are the same, we say this decomposition going to preserve all the functional dependencies. So let's look at one example, right? So assuming you have one relation zip code that contains city, content, street, and zip code, and then you decompose it into one relation contains information about zip code and street, another relation contains information of city, content, and zip code. So what are the functional dependencies you have, right? So if you look at the original relation, zip code, right? You will have, there's a functional dependency from zip code to city and content, right? So, and you have another functional dependency from street, city, content to zip code, right? And then after the decomposition, right? So first one, is that lossless? Well, this one is actually not lossless, right? So because their intersection is zip code, right? And you do not have the functional dependency from zip code to street, you do not, right? So I'm essentially, when you join them back, it's very easy for you to construct a case that you can have more tuples, right? So we'll join them back. And second is, does this preserve all the functional dependencies? So in this case, actually no, right? So after the decomposition, you are actually going to lose the functional dependency from street, city, content to zip code, right? Because there's no way you can define that. And there's no way you can define functional dependencies between zip and street, and the functional dependency between zip, city, and content that can derive the functional dependency from street, city, and content, right? So this is relatively natural to see. So this is another example of decomposition that's actually not preserving all the functional dependencies. So that's all for functional dependency, right? So this is a lecture that's relatively abstract, right? So in the next lecture, we are going to use all the knowledge that we have been learning in this lecture to define a whole bunch of ways that you can normalize a relation. We are going to define a whole bunch of normal forms, and each one of them have different properties that we can enforce in the design. So, and all of those properties are closely related to functional dependencies, okay? So we'll go back home, read the textbook, and try to understand, at least in the abstract level, how to reason about functional dependencies, how to reason about decompositions. In the next lecture, the whole thing will become much, much more concrete, okay? So that's all for today. Thank you very much for your attention, and see you guys on Friday.